Good morning. Welcome to the second day of Berlin Buzzwords 2012. I'm going to keep my speech short because we have somebody who wants to tell you more about a project called Spanner. And yeah, I'm glad that so many people showed up for the keynote. Welcome, Lloyd from Google. Thank you.
Hello, I'm Lloyd. I'm an engineer at Google. I've been there about 8 years. I want to talk about Spanner, which is a distributed storage system project we've been working on for the last 5 years or so. It's been in production for 1 year. Our first big customer is one of Google's most revenue-critical databases, which you can imagine was not good for our nerves. I'll give a high-level overview of the system. It's, obviously 5 years of work is too much for a 1-hour talk. There's a paper under review, and at some point this year, you'll get to read as many gory details as you're interested in. Spanner was really ambitious in the semantics that we exposed to users. We really wanted to get NoSQL world semantics, SQL world semantics at NoSQL scale. Relational databases are an incredibly productive and familiar environment to build apps in. And we think that Spanner is an existence proof that it's possible to scale a relational database to a global distributed storage system. If there's one thing to take away from this talk, besides the fact that we thought this was worth doing, is how we built the concurrency control system so that we can offer really straightforward semantics by default. We want app developers thinking about business logic, not concurrency. So the way we did this, we built clocks, a clock system with bounded absolute error. At best, clocks usually give you bounded rate error so that you can do things like measure out relative leases. So we built clocks with bounded absolute error, and then we integrated them with timestamp assignment in the concurrency control. And this gives us two really cool things. We know that the total order of timestamps, they're just integers, respects the partial order of transactions. So if transaction A happened before transaction B, and I'll talk about what that really means, we know that transaction A's timestamp is smaller than transaction B's timestamp. And a ton of useful things fall out of this. One of the coolest ones is that we can offer efficient serializable queries over everything. You can add up to the penny your petabyte database that spans a dozen data centers. And it might take a while to fetch and sort all of that data, but you can have very strong invariance and expect your answer to be correct. For those of you not familiar with the history of Google's storage systems, Bigtable is one of the early NoSQL stores. The paper came out in OSDI in 2006. Megastore was a system that is built on top of Bigtable. We added a Paxos synchronous replication layer and a richer data model on top of Bigtable. That paper came out in CIDR in January of last year. Spanner, in its low-level architecture, looks a lot like Bigtable, for better or worse. Updates are appended to logs that live in a data center local distributed file system. Periodically, they're compacted into immutable B trees, what Google calls SS tables. Periodically, those SS tables get merged together, and so on. It looks a lot like, there's a version of this that got open sourced for web browsers called LevelDB. But we're trying to get a lot closer to an abstraction that looks like a single giant MySQL. Developers, of course, are still going to have to think about how to partition their data for efficiency, but as much as possible, we want to let the people writing business logic think about business logic. There also had to be no downtime for repartitioning. This was a big one. Everything we do is racing with data movement, because moving users between data centers and resharding the partitions that a user might be spread across, or whatever the entity is, if not a user, is a continuous background activity. And you can imagine if everything we do is racing with this data movement, there are all kinds of concurrency warts that kept arising from that. So we really ended up having to be fixated on what our transaction semantics were, to have any hope of getting this constant background stream of repartitioning right. We ended up being a very hardcore customer of our own transactions. And I can say before we had good transactions, we had a lot of bugs. So part of why this thing took 5 years. So I mentioned we really wanted our app developers to be spending less time thinking about storage than they are now, and also to be less bound by decisions like partitioning that they made early in the design process. It was important to capture the most successful aspects of Megastore, so users really appreciate being able to write out large-scale data center outages without any user visible impact, and smaller outages of, say, specific tablets in the underlying big table. Something's overloaded, some tablet got corrupted, there's a billion reasons, the power went out on just one rack. There's a billion reasons you have little micro outages internally to a cell all the time. And Megastore has been very good at letting users ride those out where they'll see a latency bump as some timer fires and you get failed over to a different data center, but they see no impact on the semantics of the transactions. But it was also clear we had to address some of Megastore's shortcomings. The first one is you partition the database into a bunch of entity groups. And this shows up in a decent number of systems where you can think of it as millions of small separate databases. Each entity group is, for the most part, its own siloed transaction domain. So you can't, for example, do a snapshot query across a bunch of entity groups and expect meaningful semantics across those entity groups. Megastore also uses optimistic concurrency, which, when your replicas are spread, say, 50 milliseconds apart, and you're doing synchronous replication to update over those replicas, the writes are inevitably going to take, just bound by the speed of light, at least 50 milliseconds. That creates a big vulnerability window for optimistic concurrency failures. And our paper had been out about 2 hours before the first blogger who blogged about it had a big pull quote in italics that was the paragraph on the write rate you get out of Megastore and some carefully minced words like, for most of our users, this has not been a problem because blah, blah, blah. There's sampling bias there. People don't use Megastore unless they can live with that. And there are a very large number of apps who've been OK with that, but it was something we felt it was time to figure out how to fix. You can also imagine there are a lot of benefits just to consolidating these layered systems into a single integrated system. The interface between, for example, the replication system in Spanner and the physical storage is much richer and more optimized than the interface between Megastore and Bigtable can be. There was another big cultural shift at Google that's worth talking about. The SQL-based analytics system, Dremel, which we have a paper out from VLDB in 2010, made a lot of SQL converts at Google. People realized it is incredibly powerful to just push the semantics of your query down into the storage system and let it figure out what to do. And I realize it might sound silly to be making this claim in 2012, but the culture is so ingrained that you can have scale or you can have SQL. And for analytics, Dremel convinced people that you can have both. And Spanner team thought maybe it's time we figure this out for OLTP once and for all. There are also a lot of business concerns that meant that we need easier geographic partitioning. It needs to be easy to move all of a user's data from one region to another. There's an increasing amount of legal constraints on this, and also just as a product grows, you want to be as efficient as possible about how many people you put where. So here's a simplified diagram of Spanner's data model. Suppose you have a single relational table of users. Each user has a name and a home region, let's say. And that database can be divided into a couple partitions, We've got one partition in the US, another partition in Europe. In reality, a large database is going to have millions of these. And this partition 1 has 3 replicas in the US. And the orange one, let's say, is the Paxos leader. And the other partition has 3 replicas in Europe with a read-only replica in the US. This is handy so that you get a write quorum in Europe. You're never blocking on transatlantic RPC calls in front of a user, but you can still query all of the data, albeit back in time a little bit, from the US. We did not always have this relational model. Jeff Dean gave a talk at Lattice 2009 and gave a quite different picture of Spanner. I've got some slides at the end of the talk on the subject of how we got here. It has a lot of bullets. Underneath this relational abstraction is something that's kind of familiar from how people might hand encode the keys into Bigtable, or how people encode hierarchy into, as I understand it, into HBase. Each table cell is just an entry here, customer ID 1. At time 10, we created this Alice record. Somebody realized we misspelled Alice. At timestamp 11, somebody updated just the Alice cell. And it's also worth noting that master detail hierarchy gets physically clustered together. The orders for Alice are going to be stored next to Alice before the Bob record begins. This is more important in a distributed system where the odds are that records next to you are on some other server than in a single SQL database. At a high level, Spanner uses a hybrid of two-phase locking and snapshot isolation. This is something you see in existing databases, and that's sort of the point. This was really about not trying to invent a crazy new model, but just figuring out how to scale some well-proven ones. And this particular combination is good for workloads that are dominated by reads, because you spend most of your time in cheap snapshot isolation reads and not very much time messing around with pessimistic transaction locks. The idea here is supposed to be, again, that you write your app without thinking too hard about transaction semantics, just getting it right. And then you go back and optimize a few high traffic operations where the optimization effort is really going to pay off. I'll give an example from when I worked on Blogger. Back in 2006, when I was making the case internally that Blogger should use synchronous replication, I counted we had 280 servlets. There's a lot of them are low frequency, high complexity operations, like user creates a blog by sending a text message on their phone, and then they want to come back and merge that blog into their existing blog. And a pretty junior engineer spent an embarrassing amount of time writing that as a series of independent, idempotent operations in an elaborate workflow. Testing that is pretty complicated. If we had just had ACID distributed transactions, overall, Blogger would have been faster, because that amount of time that goes into these unnecessarily complicated things with no performance benefit could have gone into shaving 50 milliseconds off of some high-frequency page with a much bigger impact in overall average latency. It's the same process you do when you're programming a single machine. You start with mutexes, and only then do you reduce contention with atomic operations where it counts. In some sense, NoSQL databases that only have weak consistency are enforcing a broadly applied premature optimization on the sort of entire system, instead of letting you opt into that for the pages where it's worth it. The interlude slide. So what guarantees do we want exactly? I've been talking about sort of, well, it sounds like we want everything. I'll define what everything means. Here's a hypothetical schema to motivate the example I'm going to walk through. So we've got 3 partitions. One partition is a table of ads that people have bought. Somebody bought an ad for a camera, somebody bought an ad on puppies. And again, it has a write quorum in the US and a read-only replica in Europe, so that systems in Europe can read a stale view of this table. There's also a partition in the US of impressions of these ads. So at 2 and 201, somebody in the US viewed the puppies ad. And in Europe at 2 and 202, where they probably wouldn't put PM, somebody viewed the puppies ad again. And note how there's a read-only replica of the European partition in the US, so that from potentially a single data center in the US, you could still do a MapReduce that tallies up all of the partitions and does whatever auditing you're trying to do. Here's an interaction diagram of a common sort of distributed system scenario at Google, trying to essentialize a pattern that we see a lot. We've got the entities here are, there's an ad purchasing UI. This is the web page that you go to at Google to buy your ad. There's an ad serving system, which is whatever background machinery actually renders these ads to users. And 2 database partitions. There's one partition of the ads themselves. And for this example, we can talk about just one of the partitions that keeps track of ad impressions. So user goes up to Google. In transaction 1, the user buys this puppies ad. In the background, the ad serving system is continuously scanning this partition looking for ads to show. So it sends a retrieve ads query, and back comes this puppies ad. Then for a while, this ad serving system is serving these ads in the background, and it accumulates a batch of impressions that it wants to save in the database. So in transaction 2, it issues a write to this impressions partition to record some of those impressions. Here's what that might look like. The state of the database progressing as time goes down. There was nothing, then somebody created the puppies ad, then somebody recorded the impressions. And note, these are 2 different partitions. They're stored in different sets of replicas, potentially different data centers, potentially different continents, and so on. Suppose now you're writing a MapReduce or a SQL query to audit the ad impressions at the end of an hour. We pick some timestamp, and I'll talk later about how you can go about picking those timestamps. But one legitimate way is just pick whatever timestamp is the end of your hour and run a MapReduce at that timestamp. There are only 3 legitimate outcomes. Either it sees nothing, or it sees the ad but does not yet see any of the impressions, or it sees these impressions and potentially some prefix of the subsequent impressions. In all of the systems we're replacing, here's the key. The MapReduce or the query has to tolerate an infinite number of other variations in this ordering. It might see the impression, not the ad. And when you're trying to write a query whose inputs have such weak semantics, it's really hard to tell the difference between a bug, corruption, or a concurrency anomaly. So the way people have gotten around this, where they really needed a consistent view of a large data set, they built a specialized system that serializes every update through a single central server. In effect, there's just one partition. And this works okay if all of the updates are originating near that server. But it doesn't work very well in this sort of central design point for Spanner, which is that users and data are distributed all over the world. Here's another way of visualizing the set of legal transaction orderings. So there are 2 pairs of transactions. transaction, and this is the kind of rule of thumb that we think about always when we're designing these things. There's transaction 1 and transaction 2, and we want to preserve the fact that transaction 1 happened before transaction 2 because it finished before 2 started. So we're going to say that there's a commit order dependency from 2 on 1. And T3 and T4 have a traditional data dependency. T3 wrote Z, and then T4 read that value of Z. And so we also have to make T3 always happen before T4. But there's no relationship between the ordering of T3 and T4 and T1 and T2. These guys are concurrent, and this is where the performance of the system can come from, is leveraging its freedom to run transactions that are concurrently. So the way people think about serializability, is there a serial order that's equivalent for some definition of equivalent to the actual concurrent execution history? And for our purposes, we'll ask, does it preserve the same dependency order as the original history? And so here are 2 example serial histories, both of them preserving the T1, T2, and T3, T4 order. And of course, there are more. We talk about serializability as a gold standard of transaction semantics, but it's unfortunately a kind of overloaded term. If you're curious about all the variations people have studied, the Wykeham and Vosen textbook walks you through about a dozen variations of how they build on each other, different kinds of serializability. There's this amazing Venn diagram with like 12 nested, sometimes overlapping rectangles for the different sets of transactions that are legal under all these different definitions of serializability. There's a useful term that comes out of concurrent programming, linearizability. It's about the most intuitive, feasible model for programming a multiprocessor. And it applies well to programming a distributed system on top of a distributed database. So we need to, of course, it includes serializability. We need to be equivalent to some serial order. And we can't commute the commit order. So that was that T1, T2 dependency in the previous slide. So even when there's no detectable dependency, the system may have had no reason to think that T1 and T2 were related to each other. And even when they're executing on different machines, there's a real-time component to this definition. There's a range of options for scaling the semantics that we are looking for in a global distributed database. So a few involve lots of when communication. You can include all of the partitions in every transaction or some agent that acts as their proxy. That's roughly the there is just one partition answer. You can have a centralized timestamp oracle, which doesn't work so well if you have updates happening on 2 different continents at the same time. There are a couple options that have no extra communication. You can propagate the timestamp through every single external system and protocol. This is what people think of as Lamport clocks. And this works if you have few enough systems and few enough protocols, but it doesn't work so well when you have a huge legacy of different distributed systems. Sometimes you don't control all of those protocols because they're for transacting with trading partners or just because it's code you don't want to modify. And we've tried this a couple times at Google and never been very successful at the discipline of threading timestamps all the way through a complicated system. There was a phase where there were timestamps showing up even in user cookies. And the last option, build somehow a distributed timestamp oracle. So it turns out we had one of these lying around. There was a team that had built a system called TrueTime already. It was mostly something that fell out of a general time cleanup at Google. And what it gives you is an interval when you call now with a time and an epsilon. So you know that the real time, some point while you called that now call, was somewhere within that interval that it returns. It's derived from GPSs. There's a GPS receiver in a bunch of different data centers. And it's backed up by atomic oscillators. The GPS system does sometimes have bugs. We wrote out one push where they took out accidentally a bunch of satellites. Oops. It turned out that because our receivers have been told that they're stationary and they know their position, there were more fixed variables and they could still compute time. But it was close enough that we were glad we have these atomic oscillators. And it sounds like, oh my God, atomic clocks. Turns out these are kind of a thing you can just buy now. So talk a little more about how we're going to get these guarantees. So I feel like we've been talking about databases for a while, and we've earned a digression. Say we're sailing to Scotland, and it's 1870, and so all we have is a sextant and a compass and this thing called a taffrail log, which is just a little turbine, essentially, that you tow behind the boat. It twists a string. That string twists a counter and tells you your distance over water that you've gone. So every time it's clear at dawn or dusk, you get out the sextant, measure the angle between a bunch of stars in the horizon, look up in a big table, plot where you are, and you get a star fix. You have a pretty good idea of a pretty small error where you are. And then it's foggy for a few days, and so you're just dead reckoning. You know your angle from the compass, you know your distance over water, but let's say you don't know about the current pushing you east. So you plot on your chart where you think you are at the end of that couple days, and then finally it clears up, you get the sextant out again, and you get another star fix, and you realize, oh, there's this other current vector that pushed me that far east. Notice from this that there's a sawtooth function in your position error. Every so often, you've got some external reference that gives you position with a very narrow error margin. And then that error margin grows over time as you're dead reckoning. And then you get another external reference, and your error margin shrinks again. Our true time system works the same exact way, except that we have hard bounds on that error margin instead of just guessing. Or, they're provable bounds. So there's a daemon in every server at Google, and there's also a crystal, like every server always has. And then every data center has a few time masters with GPSs from a few different manufacturers, just for bug diversity. And some of them have atomic oscillators to cross-check these GPSs. Every 30 seconds, the daemon talks to the time masters and gets a time fix. And then in between, it dead reckons based on its own crystal, with the error margin widening as time goes on. About a very conservative one that we have picked based on what we think the real error margins are and where the enforcement thresholds are and so on, something like 200 parts per million. So a simplified version of this process to figure out what time might it be. Let's say you just had one time master you're talking to. You read what time it is on the local machine in terms of, say, the TSC. There's a little CPU counter in each CPU. And then you send a get time RPC to the time master, and it comes back and says time is T. And then you read your TSC again, and you get some delta. And then you dilate that delta for whatever you think is the error margin that you need to be baking in for your oscillator temperature excursions and so on, plus an enormous fudge factor. And back comes an epsilon. So now you can say time is in t plus e. You know time is not earlier than t because there's a causal relationship from the time master reporting t to your receiving his response. But there's a lot of slop in there because it's possible that message was sent epsilon ago. You don't know where in this round trip t was generated. So the dominant feature in the initial error before it starts drifting is round trip time to the time masters. Here's, this will be familiar if you know how NTP works. There's an algorithm called Marzullo's algorithm, where if you're actually talking to a bunch of time masters and you want to figure out what time do I really think it is, let's say we've talked to 4 time masters and we got back 4 different intervals. You go through and try to pick what's the interval that the most masters can agree on. So that interval up there with 3 masters is the one we're going to use. If you note, there's also 2 answers that overlap just a tiny bit, the first answer and the last answer. That one loses. It's also worth pointing out you could build other systems for distributing time than GPS. You could imagine just in a smaller world, you could have a blinking LED and just pulse some kind of clock to all of your systems. You could have a heart-beating system that's periodically talking to a central server, and then in between those heartbeats, all of your servers think time is stationary. GPS is there and it works, and the system is there, and because we also have the atomic oscillators to check against and convince ourselves that it works, this has seemed like a pretty good way to do this. And none of the hardware that we're talking about is that expensive. So this slide is really just a reminder of the invariant that we're trying to get. Given 2 writes, A and B, if A happens before B, meaning if A finishes before B starts, then A should have a smaller timestamp than B. And finishes is a definition you have to be kind of careful of. It doesn't just mean acknowledged back to the client, because a transaction might become visible at some Paxos slave, say, before it's been acknowledged back to the client. And the transaction B might be dependent on A because it read from this slave and saw the outcome of A. So it's really about the moment at which anyone could see the effects of the transaction A. And once we've got this invariant, it lets us say that snapshot reads at arbitrary timestamps are serializable, even if we don't know a priori what the set of snapshot reads people might try to issue are. Here's the flow that the Paxos leader of a partition goes through when it receives a commit request from a client. The request comes to the leader, start commit. It acquires transaction locks. This is the 2-phase locking part of this whole system that works the way 2-phase locking usually does. We're just grabbing read and write locks to make sure conflicting transactions are not executed simultaneously. Then we pick a timestamp that is the true now.max. So the latest time at which now could possibly be, well, a time that we know is bigger than the current time. We're going to pick as the timestamp. Of course, infinity would be a latest time that it could possibly be. And then in parallel, we're going to do 2 things. Run Paxos to get consensus on whatever the write was, and wait until the true time is definitely past that write timestamp. And typically, Paxos is going to take a lot longer than that wait, and so this adds no extra overhead. Then we're going to notify the slaves, unlock, ACK back to the client. This, I promise, is the hairiest slide in the whole presentation. This is why this works. So that first dot is the moment in real time at which transaction 1 started. And that first interval was the result of calling true time at that instant. So we picked timestamp T1 to be a time that we knew was definitely greater than the transaction start time. And then this transaction 1 was not allowed to finish committing until another call to true time would confirm that that timestamp is definitely in the past. So if by that delay, by waiting until true time can confirm that the commit timestamp is in the past, we're pushing all of the future transactions later in time into bigger timestamps that are therefore going to end up being guaranteed to be bigger than the commit timestamp of this first transaction. Transaction 2 starts. There's a happens before relationship in that transaction 1 ended before transaction 2 started. Again, we pick a timestamp, a commit timestamp that is, that should really be, this doesn't work. I can't reach. That we pick a commit timestamp that's at the end of that interval. So guaranteed to be bigger than the first transaction's commit timestamp. And that's really all there is to this algorithm. This contract between two transactions that every transaction agrees to pick a timestamp that's bigger than his start point, and every transaction agrees to defer its commit until its own commit timestamp is in the past. Here's the scenario where this costs something. When Paxos goes too quickly, or let's say there's just one replica and you're just committing to local disks, and in that case, epsilon can become significant, the true time epsilon can become significant relative to the time it takes to commit the write otherwise. This comes up if true time epsilon has spiked for some reason. For example, a bunch of time masters went down and we have to talk to distant time masters. It can happen if your Paxos replicas are, you have multiple replicas, but they're just unusually close. You've got a bunch of independent failure domains that are very nearby each other geographically. In this case, you're also lucky, in some sense. Here's what the real world epsilon looks like at the moment. It bounces between 1 and 7 milliseconds most of the time. The slope is the rate at which the error grows is, again, this 200 parts per million that we assume as the kind of worst case oscillator error. And the minimum is the latency to time masters. Here on March 31st, you can see the tail latency got a lot better. That was some kind of networking change, I think, so that the time requests were running at a higher QoS, and that quality of service was getting enforced at more layers of the system or something like that, so that essentially less network congestion was slowing down our time master requests. You can see on April 13th, things got a bit noisier. That's because some planned downtime took some time masters down, and slaves had to talk to more distant time masters. This data is from a few thousand machines sampled across the fleet, reasonably representative. Some things you can do to reduce that epsilon. You can pull the time masters more often. You can pull at higher quality of service. You really have to get, even in the kernel, there are buffers that can that are big enough for very large bandwidth delay products. And you can end up buffered for a sizable amount of time on the scale of millisecond epsilons in the kernel. So you have to make sure that you get to jump past those queues. There's some neat Linux features that let you get timestamps a packet was sent just in the network card driver, so that after all of the queuing, you can find out when your packet was sent, and there's a symmetric one for on the way back. And you can buy better oscillators, which is not as crazy as it sounds. Your cell phone has much more accurate oscillators than a standard computer, just because Computers never needed particularly accurate oscillators before. And watch out for kernel bugs. I mentioned we're sampling the TSC. In a lot of power-saving modes, you could have a different CPU speed for each CPU. You have to be really careful what you're using as the local reference in each machine. There's a singleton counter in a whole machine called an HPET, but reading that is pretty expensive. There's some subtlety there. Another interlude slide. So we've talked about what is this thing? What kind of guarantees does it give us? How are we getting those guarantees, at least in terms of the serializable read queries? But I haven't actually said much about how we actually do these reads. There are a bunch of different kinds of reads. Within a read, modify, write transaction, this looks just like it does in a standard database with two-phase locking, except it's happening at the Paxos leader, and most databases don't have that concept at that level. So we just acquire a read lock, or the client can say, for update and acquire an exclusive lock, and so on. There are what we casually call strong reads that are not a part of a transaction, but they still need to of a long-running transaction, where the client is not going to write. So we know in advance that I want to do some reads, but I promise that I'm not going to do writes that are based on these reads. And in that case, Spanner can pick a timestamp that's just guaranteed to be bigger than all previous transactions' timestamps, and then do a read at that timestamp. And there are boundedly stale reads. This is pretty useful if you've got slaves in a bunch of different data centers, and you just want to know that the data you're reading is 5 or 10 seconds old. Spanner will pick a timestamp that's the largest committed timestamp that still falls within your staleness bounds. And if at that replica, the largest committed timestamp doesn't fall within your staleness bounds, you'll have to look for another replica. Or a MapReduce, or a very large-scale batch read. And typically there, if you're doing some kind of query that is going to take minutes or hours anyway, you really don't care about seeing the absolute freshest data. So a simple thing to do is let the client pick a timestamp and say, I want to know everything as of noon. So the ways that we go about picking these timestamps, the simplest one is just ask TrueTime, what's a time that is bigger than now? And you know that that is also bigger than the commit timestamp of all previously committed transactions. This is not always the best timestamp to pick, because you want to maximize the number of replicas that are actually capable of serving a read at that timestamp. And another way we do this then is to just look at the commit history and say, pick a timestamp from recent writes. It's always safe to compress away that data because you can always just pick a more conservative, bigger timestamp. And we force you to declare the scope of your reads up front. So you can think of, if you're doing a query in a single MySQL instance, the scope is that MySQL instance. You might, in Spanner, want to say the scope is these 5 users and this range of products, or something like that. You can just dynamically cast some concept of scope on top of all of your partitions. This is all complicated a bit by prepared distributed transactions. I definitely don't want to rat hole too much into that here, but because a distributed transaction has to commit at the same timestamp on every partition, there is an uncertainty window where you don't know what data is going to commit at some timestamp for certain objects. The principles for how we think this should be used and how some users are using this. You still obviously need to design your schema for data locality. There's no getting around the fact that reading a bunch of stuff from one machine is better than reading a bunch of stuff from a bunch of machines. So you try to put a customer and her orders in the same partition. But there's a big difference here. So then your tail of big users, well, they can span partitions. And there is going to be no concurrency impact. There's no impact on the semantics of your transactions from the occasional update or read that ends up spanning these partitions. We want you to design your app for correctness, deal with the hundreds of nitty-gritty corner case operations that just have to work. They don't have to be that fast. And then how many times a day do you change your Gmail filters or something? And then relax the semantics for carefully audited high traffic queries. Spend that time. Maybe there are cases where a boundedly stale read will do. And in those cases, by all means, use that. Maybe there are cases where threading a timestamp through your app in some confined case is easy, and by all means do that. The further you're able to read in the past, the more replicas are going to be able to serve that read. But the default semantics on all of these operations in Spanner is that they are just linearizable. Our first big user, I mentioned F1. We migrated a revenue-critical sharded MySQL instance from some large, I don't remember, but a lot of MySQL servers onto Spanner. They gave a talk at Sigmod recently, and they had a substantial influence on the Spanner data model. They needed something that looked as close as possible to a giant MySQL, and the layer that they were replacing had built something that tried sort of to kind of sometimes seem like a single giant MySQL on top of this large array of separate MySQL instances. And they pushed on us hard to consider this use case pretty carefully. Spanner started out when it was really son of Bigtable and a lot of forked Bigtable code with a distributed file system metaphor. The idea was basically you had this tree of directories. Each directory was the unit of geographic placement. This directory should be in these 3 replicas in these 3 data centers in the US. This other directory should be in these 3 data centers in Europe. And that doesn't relate very much to somebody who is building a database or trying to, has been using a database. So we added structured keys to the directory names and file names so that at least the system could query efficiently for 5, 2, 7 if that's a hierarchy encoded into your file name. But it still begat the need for layers on top of Spanner. In essence, we were about to breed the next Megastore on top of Spanner. So after a lot of soul searching, we decided Spanner needed a much richer data model. And we decided it was a hierarchical store for protocol buffers. So protocol buffers are Google's structured hierarchical data format. It's a little bit like typed JSON or something. And you could think of the Spanner universe as a single gigantic protocol buffer spanning the globe with little points in the tree defining where the partitioning was okay. This seemed reasonable, but again, there was an unnecessary gap between the way our schemas modeled data and the way users were used to modeling data. So as we watched F1 building these relational schemas on top of our hierarchical protocol buffer schemas, we had to admit that the F1 schema was just a more comprehensible way to do things, and that a migration path from SQL databases was something that we should not take lightly letting go of. So we moved in the end to this relational data model. And as I showed a few slides earlier, there's already this mapping from the conceptual data model onto physical entries that are stored. And so in some sense, this was a veneer on top of the system, but it's really important to get right because it's how users think about the system. What are we doing now? We're working on polishing the SQL engine. One of the great features that falls out of these timestamps is that a timestamp plus iterator positions is enough information to restart a cross-partition query. This is pretty cool. So you're doing a big query that's going to take a minute. You're slurping in a bunch of data. And in that minute, the load balancing forces one of the tablets you depend on to move to a different server. Or that server gets preempted because you're running in a shared cell, and that preemption forces those tablets to move. We don't want to just abort that whole query and throw away the work that you've done. For one thing, because then the client has to have a retry loop around these queries and know that all of the data that it gets back is tentative until the end of the query. So we serialize the iterator positions and this timestamp, and you can restart halfway through the query. But you can imagine when there are different server versions running, keeping that deterministic on either side of the restart is incredibly complicated. A new server ran half of your query, and then an old server comes up and tries to pick up where it left off, and it has a subtly different sort or something. So nailing this down is really valuable and hard. We're doing general hardening work. I've talked a lot about concurrency. By far, the bulk of the work in this is just distributed systems work. Fine-grained control over memory usage so that when a bunch of servers are all depending on each other, you're not going to create a distributed deadlock where they're all out of memory to make progress, but they all need to make progress to free that memory, that sort of thing. Finer-grained CPU scheduling. I want to keep the fast queries fast, even when one big query that's hopelessly slow comes in, and we should time slice the hopelessly slow query to make the fast queries stay fast. Keep the latency tail in. The strong reads that are just based on snapshot isolation are still pretty green. We're getting those into production sort of in incrementally more use cases. And scaling to large numbers of replicas per Paxos group. So you can imagine you could use a spanner partition as a strongly ordered pub/sub scheme where you've got read-only replicas all over the place of some partition, and you are trying to use it to distribute some data in an ordered way to a lot of different data centers. That creates some different challenges in terms of, what if you're out of bandwidth to some subset of those data centers? You don't want the data to be buffered in the leader server too long. So if you spill it to disk, then you have to seek to get it again when that bandwidth constraint goes away. There's a lot of it almost becomes hydrology, where you've got all of this data going to different places at different times, and you're trying to keep the flows manageable so that the system keeps running smoothly, and smoothly means fewer server restarts, means better latency tail, means better programming model. And that's all of the slides. Thank you, guys. There's a few minutes for questions. And somebody is running around with a microphone, I think. This is taped, so we'll try to get the questions on the tape as well.
Yeah, I'd like to ask a question. With a lot of clock synchronization methods, you might have strong local consistency and a weak global consistency, for instance, NTP. Mm-hmm. Is it possible with this to weaken the guarantees if you know that all the resources you're updating are local?
You could imagine doing that. We've talked about that as a sort of, say you've got this case where all of the replicas are very near each other and they're backed by flash, and you ought to be able to get, order millisecond writes if you weren't waiting around for this sleeps around 2 epsilon. You could cave and say, we're going to create separate transaction domains. There's local consistency here, there's local consistency over there. That would work. It's something that we're resistant to because it just adds an asterisk to our transaction model.
Doesn't it still guarantee the partial ordering on timestamps? Because the partial ordering just has to be relative to whatever timestamp offset is in the data center.
Right, but then we have to say, you can't move this partition to a different data center that's in a different time domain.
No, I mean, doesn't it preserve your global constraints? Because your local updates all have the correct constraint, and the ordering relative to global other data centers doesn't matter because by definition, there's no dependencies.
How do you prove there's no dependencies is the problem. I do
Because it's a local update with local reads.
But then after the result of those reads gets emailed to somebody who clicks on a link, the handler for which link is serviced by some server in some other data center that then does a write. It's very hard to say that there is no causal dependency between transactions in two different data centers. And we want you to be able to relate the ordering of transactions across the whole system on this sort of assumption that there could be causal dependencies between them. Does that make sense?
Yeah, it does. I was just trying to do an inductive proof that if the inputs are well ordered.
It gets back to that case early in the slides with the transaction, one transaction creating the add and another transaction creating the impression, recording the impressions for that add. As far as Spanner knows, there could be no relationship between these two tables. And we still want to preserve that ordering because some complicated chain of events in an external set of distributed systems creates a dependency between those two transactions. This is a really good question. This is the key to this whole thing, and is the question people always ask us, why, do you really need this?
You just answered my question.
Okay.
It was exactly the same thing. I was wondering why, given that you're doing strict two-phase locking, you gave up on Lamport clocks.
Right. It's really hard to thread the Lamport timestamps through the whole world. And it is absolutely true that if we were able to do that, there would be no need for this time synchronization.
Hello, I have a question. Since you said that you have to wait the epsilon interval before you start the next transaction, this means that you have at most 1/epsilon transactions per second.
In that thread.
In that thread, exactly, whoever said that, thanks.
Okay.
And it's actually 2 epsilon because you pick a timestamp that's now plus e, and then you have to wait until now minus e is bigger than that timestamp. So it's true that a single dependent chain of transactions can commit no more than, at a rate of every 2 epsilon. But all of the other stuff that's happening concurrently to those can do whatever it needs to do.
Sorry. If you have 2 nodes, for example, could it be possible that
Sorry, where is this coming from?
yeah, here.
Okay.
Yeah. If you
Right
have,
up here.
Yeah, if you have 2 nodes, for example, that get their time from true time, could it be possible that they get that exactly same time for 2 very different transactions? And what happens if they get exactly the same time?
Each partition is going to assign that same timestamp to those 2 different transactions. And that's okay. A read at that timestamp will see both of those transactions. A read at that timestamp -1 will see neither of those transactions. And I glossed over one detail. If you're on a single partition and 2 transactions, let's say, get the same value of the true time, it's still monotonic within a single partition. Any other questions? Somebody over there?
This sounds similar to another problem I heard from another colleague. I mean, have you evaluated PTP, for example, or using the time of the fiber optic frequency of light to synchronize?
One of my colleagues, the guy whose baby this true time system really is, came out of the networking group at Google. And he is always talking about ways to piggyback on the networking system to efficiently distribute time. It is something that may make sense someday. It's an interesting question. I think for now, it was only recently that we really understood how useful this was, and knowing that it's worth thinking about what are more reliable, lower latency ways to go about disseminating time. One of the things we're leery of is depending on router bugs. And the more pieces of the system that get their hands on some semantically meaningful part of the signal, the messier it is to reason about how much do we trust this thing.
I can confirm you they bypassed, for example, the kernel because that introduces latency. So that's another thing that...
Thanks, these are great questions.
Since the epsilon is measured on a normal clock, it will have an error itself. Mm-hmm. So do you have an epsilon, or how do you solve this?
Yes, we have epsilon. So when we read the TSC register before sending the message, what time is it, to the time master, and then we read it again after we get the response. And that gives some number of clock ticks that happened in that interval. We scale that by what we think is this hard-coded worst-case error margin, currently 200 parts per million, and use that as the number of clock ticks. Separately, there's a system that before actual measured error gets anywhere near 200 parts per million, flags this clock as bogus, and the machine gets sent off and gets a new motherboard or a new oscillator or whatever. So yes, there's epsilon. Any other questions? And so one of the ways we're looking into to reduce epsilon is just buy better oscillators.
So it sounds like you have lots of complicated logic about, or maybe not that complicated, but you have this elaborate tracking of dependencies between different interactions. I'm wondering if you've encountered any particular problems with real world cases that have a high degree of fan out or fan in terms of the number of reads or writes that are causally dependent on some earlier event.
There's two answers to that question. When there's this dependency that just arises from real time, transaction 1 finished before transaction 2 started, nothing is explicitly tracking that. We're just looking at what time is it when we assign timestamps so that the timestamp order will reflect any set of dependencies that may have been created by a real-time ordering. It's also, if you do a distributed transaction that touches a zillion partitions, there has to be coordination where they all commit at the same time and they're all negotiating prepare messages in the standard two-phase commit. And there are certainly scaling problems where, once you have hundreds of partitions, you're sitting on locks for a long time. You have to keep alive so that everybody knows you're still making progress. You shouldn't abort the thing, and so on. But is that clear about the sort of assumed dependency? We don't need to keep any actual state about that. Over there in the middle.
In the time where you are waiting for the second timestamp, are you spinning or are you rescheduling?
Are we spinning or are we?
Rescheduling.
Yes, we're rescheduling, and we end up oversleeping, of course, because of that rescheduling. We have stolen a guy from the kernel team, and one of his jobs is to help us figure out how to oversleep less. In the more oversubscribed a machine is, there might be a span server and some other stuff working, or within that span server there's a zillion threads doing more work than there are CPUs. It's of course easy to not get woken up when you wanted to get woken up. We really view the case where you have to actually spin for true time as a backstop that has to be there for correctness, but we want to design things such that we don't end up in that case very often. It's not good for latency. Someone up here? If there's someone I can't see who's persistently had a hand up, raise 2 for the next round.
Hello. Oh,
Hi.
I'm sorry. Excellent presentation.
Thank you.
Quick question. So clearly for ads project, for instance, they're so tied to relational data model, so it's very hard for them to migrate to like Megastore. But for new projects at Google, who have a choice and have a decision to make whether to use Spanner or use Megastore, like how do you help them make this decision? What is the criteria, essentially?
It's mostly one of support resources for now. We have certain high priority customers that we have to give a lot of love while we harden Spanner more so that they don't see our warts as often. And so we try to add new customers who are ones who really definitely clearly need some feature of Spanner. Somebody who needs SQL queries with complicated like geographic arithmetic, or somebody who really needs the distributed transactions or really needs the snapshot MapReduce or something. And then we work with those customers to make sure that we've nailed the user interface for that. In the background, the Megastore people are all trying to figure out how to make the migration to Spanner as smooth as possible. Which was there's a lot of 6 of one, half a dozen of the other kind of decisions where the Megastore people are good at being like, guys, there's already a way of doing this, just do that. I should mention, I was bummed I missed this talk at the end of yesterday. Somebody was talking about concurrent data structures, which I think are the sort of extreme other way to go about solving these problems. If you're building a new system and you're not dependent on SQL and ACID transactions and so on, can you just be resilient to eventual consistency in some rigorous way? And the case where you have a lot of mobile clients all trying to update offline caches of data that eventually is going to get filtered asynchronously back to Google is a case where you hopelessly have to, you can't depend on this rigidity of global ACID transactions. You have to have a rigorous way of ordering conflicting updates. And Google Docs, the concurrent editing in the Google text editor is a good example of this. You've got 5 windows open. They're each making local updates. Those updates are asynchronously bubbled back to the server, and then there's this operational transforms algebra for merging those updates. And only then does it get applied by some more standard database transaction to the canonical copy of the database. I think there's room for both of these solutions. Is that it? Great. Thank you, guys.